Now we will discuss the Fourier inversion formula. So we have shown that the Fourier transform maps S into S, it is a continuous linear map, and now we will show that in fact it is an isomorphism of the Schwartz space into itself. So we start with a lemma. So this is called the weak Parseval relation. Okay, so let Fg belong to S of Rn, then integral over Rn f hat psi g psi d psi equals integral over Rn f of x g hat x dx. So recall that if f and g are in S of Rn, so are f hat and g hat, and S is contained in L2. So if you can always integrate the product of two functions, there is no problem. So proof. So this is just an immediate consequence of Fubini's theorem. So you have integral over Rn f hat psi g psi d psi equals integral over Rn g of psi integral over Rn e power minus 2 pi I x dot psi f of x dx d psi. Okay. Now e power minus I f x is of modulus 1, mod f and mod g are all L1, L2 and so on. So the product is are in L1, and therefore the product is in integrable in the product measure, and therefore by Fubini's theorem we can invert the order of the integration. So this is equal to integral over Rn fx integral over Rn e power minus 2 pi I x dot psi g psi d psi and then a dx. Now this inner integral is nothing but the Fourier transform of g in the variable x, that is all. So that is equal to Rn. By definition this is fx g hat x dx, and that completes the proof of this particular lemma. Okay, so now we have the important theorem. So theorem. So this is called the Fourier inversion formula. Okay, so let G belong to S of Rn, then G of x can be expressed, you can recover G from its Fourier transform. So that is what we mean by Fourier inversion, and that is a very beautiful formula, e power 2 pi I x dot psi g hat psi d psi. So you see how nice it is. F g hat is e power minus 2 pi I x dot psi gx, and this is just a conjugate map. So this is g of x is e power plus 2 pi I x psi g hat psi d psi. So okay, so this is proof. So let phi belong to S of Rn arbitrarily, and let lambda be greater than or equal to 0. Define f of x equal to phi of x over lambda. Okay. Then of course f also belongs to S of Rn, no problem. You have only rescaled the function, so it will continue to decrease rapidly at infinity, and you have already seen what is f hat psi. F hat psi is nothing but lambda power n phi hat lambda psi. This is what we have already seen. This was left as an exercise, and we used it also later on. Okay, so now we apply the lemma. So by lemma, namely the weak Parseval relation, you have integral over Rn g psi f hat psi, that means lambda power n phi hat lambda psi d psi equals g hat x phi of x over lambda dx. Okay. So on the left hand side we make a change of variable, we make lambda psi go to psi, and therefore this will become so if you change a variable, so you get that this is integral g of psi over lambda, lambda power n d psi will be the new this thing, and this be phi hat psi d psi, and that is equal to integral over Rn g hat x phi of x over lambda dx. So pointwise g of psi by lambda goes to g of 0 as, and phi of x over lambda goes to phi of 0 as lambda tends to infinity. Okay. And phi hat, g hat are all integrable functions. So by the dominated convergence theorem, so once again the dominated convergence theorem implies that if you let lambda tend to infinity, you get that g of 0 integral over Rn phi hat psi d psi equals phi of 0 integral over Rn g hat x dx. So now I take phi of x equals e power minus mod x square. Then what is phi hat psi? Phi hat psi is pi to the n over 2 e power minus pi square mod psi square. We have made this computation, and it is a simple matter to check again by a change of variable that integral phi hat psi d psi equal to 1. This follows from the fact that integral over r e power minus x square equals root pi. So we have to just use the expression and then make a change of variable here, and then you get that this is true. So if you apply all these things, you get g of 0 integral phi hat psi is 1 is equal to phi of 0. Phi of 0 is also 1. So phi of 0 is also 1, and you had integral g hat x dx. And anyway, let me write this as integral over Rn g hat psi d psi over R. So the Fourier integral formula is true for x equal to 0, because if you put x equal to 0, you get g of 0 is integral g hat psi d psi. Okay, so that is recovered. So now what do you get? You have to take if x belongs to Rn, then apply this result to tau minus x of g. So you get g of x will be integral tau minus x g hat psi d psi over Rn. Okay, g of x is nothing but tau minus xg. So g of x equals tau minus x g at 0, that will be g of x, and that is equal to by whatever we proved, and that is nothing but integral over Rn of e power 2 pi I x dot psi g hat psi d psi, which again the properties of the Fourier transform, we saw how the Fourier transform behaves with respect to translation. So this completes the proof of the Fourier inversion formula. Okay. Corollary: the Fourier transform is a topological isomorphism of S of Rn onto itself. So we have proof. We have two maps. One is the Fourier transform, which is, and the other is f bar, let us say, which is both of them going from S of Rn into itself. I have f of xi is equal to integral e power minus 2 pi I x dot xi f of x dx over Rn, and f bar of xi equals e power integral 2 pi I x dot xi f of xi f of x, sorry. Dx. So we can show again f bar is from S of Rn to Rn, S of Rn to S of Rn continuous. Same proof as for f. F is the usual Fourier transform. We saw this that it maps S of Rn into itself. There is nothing changes because of the sign change in the exponential. Nothing at all changes, that is still the modulus 1. Everything will go through. So identical proof, there is no change in the proof. So both of them are continuous. And also we have that f composed with f bar equals f bar composed with f equal to the identity map on S of Rn, and that proves the theorem. Okay, so this completes the proof. Now we can strengthen this corollary further. So we have another lemma. This is called strong Parseval relation. So if you have Fg in S of Rn, then integral over Rn of fx g bar of x dx is equal to integral over Rn f hat xi g hat xi bar d psi. So proof. So G belongs to S of Rn, and so this implies that G conjugate also belongs to S of Rn. Nothing changes in the decreasing decay properties of that function, and therefore by Fourier inversion there exists a H in S of Rn such that H hat equals G bar. So we can always find the inverse. So G bar is the thing. So H is nothing but e power 2 pi I x xi G bar xi d xi. Okay, so that is all that you have to put for H of x. Okay, so H hat is equal to G bar. Then by the weak Parseval, what does that imply? That says that integral over Rn fx gfx dx is nothing but integral over Rn fx h hat x gx which is equal to integral over Rn f hat xi sorry, not gx here, dx. F hat xi g oops, oh sorry, this is correct. So f of x h hat x fx g bar of x here, that is correct, equals fx h hat x dx. Now that is equal to f hat xi h of xi d xi. But what is h of xi? By the definition of the Fourier transform, h hat equals g bar. So this is equal to, so by Fourier inversion, this integral over Rn e power 2 pi I x dot xi into h hat xi, which is g bar xi d xi, which is equal to integral over Rn. I can take the e power minus 2 pi I x dot xi and gf xi d xi, and that is what is under the conjugate sign is nothing but the Fourier transform of g. So g hat bar of xi, and therefore you have integral f g bar dx is equal to integral f hat g hat bar d xi. Okay. So that proves the strong Parseval relation. So corollary, f belongs to S of Rn, then norm of f in L2 is the same as norm of f hat in L2. That is obvious. Put G equals f in above lemma. Okay, so norm of f equals norm of f hat. This leads to the following important theorem. So theorem, and this is called Plancherel. Plancherel's theorem. So there exists an isometry. Isometry means continuous linear map which preserves the norm. Okay, norm P from L2 of Rn to L2 of Rn, which is surjective and such that P of f equals f hat if f belongs to S of Rn. So you can extend the Fourier transform to L2 now. So this is what this theorem does. So we could prove only for L1 we defined the Fourier transform for L1. Then we went to the Schwartz space. We proved this corollary above, which says that the Fourier transform is a L2 isometry on the Schwartz space, and from that we are now going to show that you can extend it to a isometry on L. So this we call the Fourier transform on L2. Okay. Okay. So the Fourier transform, so proof, f from S of Rn to S of Rn is an L2 isometry. But S of Rn is dense in L2 of Rn. Again, this is because D of Rn is contained in S of Rn, which is contained in L2 of Rn. Therefore, this is dense, we know, so the S of Rn is automatically dense in L2 of Rn. So implies there exists a unique extension P of F to L2 of Rn. Okay. So this means what? That means P of F equals F of F equals F hat for all F in S of Rn. Now we only have to show that P is an isometry. So norm PF, so let F belong to L2 of Rn and let Fn in S of Rn, Fn converging to F in L2. Okay. So norm PF in L2 is nothing but limit n tending to infinity by continuity norm Pfn in L2. But Pfn is nothing but Fn hat. So this is limit n tending to infinity norm Fn hat in L2. But Fn hat for the Schwarz space function is same as norm F. So this is limit n tending to infinity norm Fn in L2, and that is nothing but norm F in L2. Therefore, norm Pf equals norm F. So P is an isometry and it implies that P has closed range. But S of Rn is in the range of P. Because F is a isometry from is a isomorphism of S of Rn into S, and P restricted to S is nothing but F, and therefore S of Rn is in the range of P, and therefore you have that range of P has to be L2 of Rn. It is closed range and contains a dense subspace, and therefore it has to be the whole space. Okay, so this completes the theorem. So it's a surjective map and it's an isometry. So P from L2 of Rn to L2 of Rn is called the Fourier transform defined on L2. So caution, if F is in L2 of Rn, we cannot write F hat psi equals integral e power minus 2 pi I x dot psi f of x dx, because this integral is not well defined, because if F is in L2, it is only defined if F is in L1. But we have extended it by density from S of Rn into uniquely to the whole of L2 of Rn as an isometry. Okay, so that you have to know. So we have our next thing is to now use all these results to extend it to a class of distributions.